All right, so we have some really cool stuff to kind of end our time with this week. I am going to do section 7.4, 8.2, 8.3, 8.4. I may also put up a video about 8.1. That's actually a review of complex numbers, and I'm kind of assuming that that section you've pretty much done most of it, but it might be a good idea to review that section. I'm not going to formally give an assignment about it, but I'm just going to post a video about it. Um, just as a review. And then also 8.5 and 8.6, I'll probably make videos for those, but I'm going to give some kind of bonus assignment if you are interested, or like one extra quiz that you can do if you want to take a dropped quiz. You can watch the 8.5 and 8.6 and do that. It's going to sound like a lot, but I made the assignments a little shorter this time, and I think this is a pretty interesting week. So, what are we talking about in 7.4? So this section is about vectors, and I'll split it into at least two videos. I'm hoping for two, but we'll see how this goes. So, to give you an idea what a vector is, if you haven't had physics, so you have something like a velocity or acceleration or force. Those are all vector quantities because they have a direction. So and a magnitude. Like if I say that the wind is 15 miles per hour and I'm playing golf, that doesn't mean a whole lot to me. It's 15 miles per hour east or northeast or southeast. So there's some direction and there's some magnitude as well that we're talking about. And so, definition, so this would be a quantity with direction and magnitude. Okay. Contrast that with something like a scalar quantity. And I could just say that's a quantity with magnitude. Okay, so something weighs 10 pounds, or there's just something, one number associated with it as opposed to a vector, like a wind or a force of like 10 newtons downward, or some angle applied at some angle. So that's a kind of the intuitive distinction between vector and scalar. We want to talk about how we're going to draw vectors um, in math, how we're going to write them. There's some notation and a lot of some terms and some things we can do to vectors, different vector products that we can look at. Okay, so first thing is, if I draw a vector, it's going to look like a directed line segment. So it's just going to look something like that. And typically there's an initial point and a terminal point. So initial point is the point where I just have the point, and then wherever the arrow is, I have this terminal point out here somewhere. Okay. So in theory, I have a point, maybe x naught, y naught. That's my initial point, and maybe I have a terminal point to say x1, y1, or something like that. Okay. This textbook doesn't use a lot of notation of finding vectors between terminal points and initial points, so we don't have to use that notation too much. So instead, I'm just going to leave you kind of with this. They typically write a vector like u, and they write it in a boldface type. So in the textbook, it will be bold, and that boldface letter stands for a vector. Now, a lot of textbooks, or if you're writing it on paper, it's hard to see that it's bold. So you might get confused on whether it's a vector or not. So a lot of the time, you'll see that. It's like a little harpoon, not quite a full arrow that stands for vector U. Okay? they don't use that in this textbook, so I'm not going to use it. But just know that when we're talking about this, that it's talking about a vector u here. Okay. Now, another way I could write out that vector u, if I actually have an initial point, let's say O and say P, then this would be like vector OP. Okay, so you remember when we had arrays, talked about array? It's like how you would name an array, only it's like a vector. Okay. And it is actually different from array because it stops here. It doesn't keep going at all. And my initial point is O, so that's got to go here, and my terminal point's P. If I wrote vector PO for this picture, I would be wrong. However, for this picture, say I have P and then my terminal point's O, there this would be vector, say, PO. And that would be correct. Okay. Typically, we're not going to use this notation, but I would just want you to be aware that that is what we're talking about when I have the initial point and the terminal point, that I would write it out like this. Typically, I'm going to write something like vector u. And this initial point can theoretically be anywhere in the coordinate plane. Terminal point could theoretically be anywhere in the coordinate plane. Okay. What I really want to do first with the vectors, before we get too far in talking about other things, I want to just show how you can add them kind of geometrically. All right. So I think that's a good place to start. And this is in the book here. They give you copies of vectors. So I just want to give you, say, a vector A. And again, that's a vector A, even though I'm not writing the little harpoon. And say a vector C. All right. Now, what we can do with those vectors? Well, we can add them together. We could, say, subtract them. We could multiply by one by some scalar. Okay. And then I could get a different vector as a result. Okay. So I first want to look at vector addition. And this was called the triangle method. So it just says find, say, A plus C. How do I find the vector A plus C when here's my vector A, here's my vector C, right? So first what I want to do is make a copy of vector A the best you can, kind of replicate that vector. So same length, same direction, same everything. So that's like my vector A. And then make a copy of your vector C. Now with your vector C, since you're adding it to vector A, you're going to put the initial point of vector C on the terminal point of vector A. So your initial point of vector C would go here and would look something like this. So here's your A, C, you put the initial point on the terminal point of A. And then when you do that, the vector that you get when you add these, so if I add these two, the vector that you get as a result would go from the initial point of A to the terminal point of C. So it would look something like this. And I'm making this a different color to show that this vector is the result. That orange one, or maybe I should make it blue so you can see it a little better. This vector here is A plus C. And that's called the triangle method of adding these. And that's it. So if I give you these two vectors and I say add them, I'm expecting, maybe this kind of picture, that would be the triangle method. This would be our vector that we get by adding those two together. Okay? Right. That's called the triangle method. I also want to show you a parallelogram method. So how do I add A and C by using this parallelogram method? Well, I would first put a copy of A down. So there's A, let's say. And I would put C down, so make a copy of C, same direction and length. But when I'm doing the parallelogram method, I actually put the initial point of C at the initial point of A. So for this method, I would put C, try to make it the same direction and everything. That looks about right. It's not a perfect science there. We're just trying to get an idea. And then in order to add those two, I kind of make a parallelogram out of this. So what I would do is I kind of mirror C. So there's C. There's a parallelogram, and mirror A. I kind of draw a little parallelogram. And then to get your vector A plus C, it just goes from this initial point here to the opposite corner of the parallelogram, and this is A plus C. And if you do that right, we should get about the same thing we got with the triangle method. And this is our vector here that is a result of adding those two. Okay, so that's adding, say, two vectors with either the triangle or parallelogram method. Well, how could this get to be a little bit more difficult? Well, they could ask us to do something like A minus C. So let's do that. How would we do A minus C? And let's do that in two different ways as well. So let's do triangle method. And we'll do the parallelogram method as well. Okay. So first thing I would do here is I want to think about, if this is C, what is minus C? Well, minus C is just a vector that I get when I flip this the other direction. So if I have C, maybe it's important to note that minus C is going to look something like that. All I'm going to do is just flip it around. And then when I think about A minus C, what A minus C really is A plus a negative C. Definition of subtraction. And then if I'm using the triangle method, let's see, this is our vector A. So again, I make a copy of that. And that's to label our A. And then where does negative C go? Well, negative C, that vector, should go, if I'm doing the triangle method, should go at the terminal point of A. And it's this vector here. So if that goes at the terminal point of A, then it's going to go somewhere like this. And maybe I drew that a little bit too long. I think I drew it a little bit too long here. So I have something like that. Now, so I've got my A. So I hope you see that from A. I put my minus C, I put that on the terminal point of A. And then what's my result? Well, result goes from initial point of A to the terminal point of my minus C vector. So it's going to look something like this. So this is A minus C. That vector here, this one here, is A minus C. Okay. But we get about the same thing by looking at the parallelogram method. Well, let's see. So for that one, again, parallelogram method, I'm going to copy A. And then we are going to put minus C at the initial point of A. So that is going to be going, say, down here. And then we are going to make our parallelogram. There's my blue marker at. So I extend, so parallel to this. And now, some vector like that. So remember, I go from my initial point here to my opposite corner of my parallelogram. That was a minus c. So I think we got something fairly similar to what we got before, right? So it's all when you're drawing this out, it's important to try to be as accurate with drawing kind of the lengths and the directions of the vectors as you can. On paper, you could kind of trace it when you're doing this, so it would help a little bit. I think I got pretty close to what I had there before. I think it was like right here, and pretty similar. But just there's a little error involved, so it doesn't have to be perfect. But that's kind of the method. The method is important for how I would add these two together. Okay, so that would be our resultant vector a minus c. What about if I just wanted to make a scalar multiple of 1? So let's do a couple examples. Let's find 3a. So really all you would do here is to find 3a, I would basically take a and I would multiply its length by a factor of 3. So it would be where I would have like 1 copy, 2 copies. Well, I need more room. 1 copy, 2 copies, 3 copies. It looks something like that. Or if I wanted to find, let's say, negative 2c, I would flip that vector around, and then instead of 1 copy of c, it would be 2. It would be negative 2c. And try to draw it as straight as you can there. All right, so that's a little bit about how I would add vectors, multiply by a scalar multiple. Okay. Let's look at position vectors. So position vector is a vector with initial point at the origin, written with angular brackets, so like this. So I will kind of write that down and I'll give you an example. So this is a common notation for vectors. And when I write them with these angular brackets, we know that we're talking about a vector where my initial point's at the origin, my terminal point's at wherever that position vector is. I'll kind of draw some examples so we know exactly what we're looking at here. Okay. And for this, probably turn on my projector. Okay. Okay, so let's look at the vector. Let's say we're looking at the position vector 3, comma 4. So what would that vector look like? Well, my horizontal length is 3, my vertical length is 4. So it'd be like I was plotting, initial points at the origin. If I were to go 3, 4, and this would literally be my vector 3, 4. Okay, and what we mean is that the terminal points at this point 3, 4, initial points at 0, 0. Okay, maybe I even give that a name. Let's say U. That's my vector U. Let's do another example. Let's say I have the vector, let's say negative 2, 6. Let's call that one V. My V is just going to be like a really pointy guy. So negative 2, 6. And that's what we're talking about when we have those position vectors like that. So I'm thinking about that vector in the plane. Right? So what I want to do is I want to introduce something called the magnitude of the vector. So for a position vector, U, let's say equal to, say, AB, its magnitude. Now, we're going to introduce the magnitude. If I'm talking about the magnitude of the vector, I put what looks like an absolute value symbol around this U. It's also known as the modulus of the vector. I correctly call it just the magnitude. And it's not the only symbol that's used for this, but this textbook uses this like absolute value looking symbol, and it's called the magnitude. So that's the symbol that we're going to use. So the magnitude of this vector U, I claim, is just the square root of a squared plus b squared. Okay, so where does that come from? Why is that the magnitude of the vector? Well, if I have any random position vector, say U, and it has a horizontal component A and a vertical component B, then it's going to look something like that, right? And if I'm talking about the magnitude or the length, then the Pythagorean theorem applies. So the magnitude squared, like our c squared, is equal to, say, a squared plus b squared. If you think about this magnitude as representing the length of the vector instead of the vector. So that might be maybe the part that's a little weird. When I write this like this, that's the length of the vector. So then I can apply the Pythagorean theorem. If I just wrote this like a U, that stands for the actual vector itself. It's not a real number. So I think that's probably different, something to kind of keep in mind. It's a little weird. But then what's my magnitude? Well, my magnitude squared is a squared plus b squared. So my magnitude of my vector U is just the square root of a squared plus b squared. And another thing that we're going to define, we're going to talk about the direction of the vector theta. And we're going to use angle between, we're just going to go ahead and do this in degrees. So the direction of the vector theta is the angle, I should say counterclockwise for positive, is a counterclockwise angle between 0 degrees and 360 degrees. Kind of defined in the same way that we did at the very beginning of the course. Okay, so let's look at an example of a couple of these just to show you what I mean. So this one just says, and you can draw a picture. You don't have to. It's not absolutely necessary to do that. But this one just says, find the magnitude and direction of, say, 15, -8. And they don't use a letter for it, but we could if we wanted to. Let's call it U. Okay, so you could make a sketch. Here my coordinate plane doesn't go out 15, but I'm going to pretend it does, and I'm going to pretend that it goes out 15, -8, somewhere down here. 1, 2, 3, 4, 5, 6, 7. Okay, at least that's good. And this is our vector U. So if I do that, then really this is 15, and this is, say, -8. Kind of define in the same way that we looked at. So when I'm talking about the magnitude of U, that's a simple formula. That's like finding our R that we talked about earlier in the course. So that is just the square root of this A squared plus B squared. So square root of 15 squared plus -8 squared. That should be, so the magnitude of the vector is 225 plus 64 square root of 289, that's 17. So that's our first answer. And then what is the direction of the vector? Well, to find that, I'm actually talking about this angle here, positive angle there, right? So to find that, you have to think a little bit about what is this angle going to be? And if I know what this angle is, how can I find this angle? Because this is the angle when I'm talking about measured from the positive x counterclockwise, the angle between 0 and 360. I'm talking about this green angle right here. Okay, so to do that, I'm going to call this angle theta, and then we're going to use some trig. So I know that the tangent of theta is, say, -8 over 15. And in order to find that angle theta, I'm just going to do the tangent inverse of this. Okay. So when you do that, you want to make sure you're in degree mode if you've been in radians some of the time. And it's -28 degrees. But since I want I'm talking about the positive angles here, -28 degrees. There's a couple different ways I could think about this. One, I could say find my coterminal angle with that, so just add 360. Or I could think about, well, this angle is really 28 degrees if I'm looking at the positive angle. And then to get this angle, I'm going to do 360 minus 28. Right? And that's going to give me a direction angle of 332 degrees. Okay, so for that, you got two answers. Hopefully write each one of them out. Let's do another example with that. Maybe we should do one that's got a radical in the answer here, just to see how that would be. So find the magnitude and the direction. Here are vectors -4, 4√3. So we've got -4, 4√3 is bigger. Maybe somewhere out here, our vector u. And we've got negative 4 and then 4 root 3 here. So I would find the magnitude in the same way. So the magnitude of u is the square root of negative 4 squared plus 4 root 3 squared. So our magnitude of u is square root of 16. 16 times 3 is 48. So should be magnitude of u is just 8. Go through and compute that. What about the direction? Well, here, I could call this theta again. And I could say that the tangent of theta is, say, 4 root 3 over negative 4. Tangent of theta is negative root 3. So I could do the tangent inverse. Of, say, negative root 3. In degrees, we know that's negative 60 degrees. So really, this angle is like a 60-degree angle, though, in that sense. Okay? And the angle that we want is really this angle anyway. So if this angle was like negative 60 here, what is this angle really here? Well, it's 180 minus 60, if you want to think of it that way. So it's a quadrant 2 angle. So the direction angle is really 120 degrees. So you might think about, well, why does this give out negative 60, and why did I just kind of write 60 instead? Well, really, I'm just looking at the positive angles here. And what I'm saying is, like, this angle is really 60 degrees between this terminal side and this x-axis here. If I call it a negative angle, that just means that it's going the opposite direction. So maybe it's really thinking about this angle instead, going clockwise. Since we're after the direction angle, we really just want to think about this angle being 60 and then finding what this angle is. The reason why I'm getting negative 60 is because of the restrictions on the range for my tangent inverse. The output was always going to be between negative 90 degrees and 90 degrees. And here, I have an angle that is in quadrant 2, so it's a little different than being in quadrant 4 or 1, where I could actually have a negative 60-degree angle per se, like down here maybe. Okay, so that's just kind of something to think about. It's due to the fact that I've got kind of range restrictions with my arc tangent there. But I hope that makes sense that the direction angle is 120 degrees in this case. Okay, I think that's good for this first video.